with that, I get to present the afternoon's keynote. Our keynote speaker is Neal Ziring from the NSA. Oh, yeah. Yes, you will get to see more than his hand.
I'm teasing.
Oh, we can slide it over.
Oh, there we go.
Oh,
wow, that's cool how it does that.
Neal is the technical director of the NSA Cybersecurity Directorate. He has a long history at NSA doing pretty much everything in
cybersecurity stuff
and information assurance and everything else. And I could read your entire bio, but that would take your entire thing. With that, Reagan, would you like to put up the slides? And there's your slides.
Okay.
And I'm going to move this thing slightly over. Hope it's the reverse direction.
Put the other way. There it goes.
There we go.
I could just move this.
It's
using that camera. Okay.
There you go.
Oh, no wonder you had this tilted down. Okay. Right. Well, good afternoon, everybody. Like Dr. Taggart said, I'm Neal Ziring, and I'm the Technical Director of the Cybersecurity Directorate here at NSA. And I'm going to talk to you this afternoon about the science of composition, which I think is a good match to one of the themes of HotSoS this year, securitability and composability. I'm going to focus more on the composability part, kind of taking the desire of securitability as a given. And like Adam said, I've been at NSA 33, 34 years, something like that now, most of that in cybersecurity and the various things we called it before we called it cybersecurity. So let's see. Let's go to the next. Can I do next slide, or does Regan have to do it?
You can do it.
Okay. Oh, I see. Yeah. Okay. So modern systems. Think about how our systems are built today, right? They're all composites. They're all compositions of different chunks, right? Their pieces have dependencies. We use these things without completely understanding, in many cases, how the pieces fit together. And they are typically built or secured with informal or ad hoc rules, right? I would maintain that we do not really have a scientific basis for how to compose things in a rigorous way so that security properties are preserved or created. And this leads to surprise. This is a big factor of a talk I gave a few weeks ago to a seminar on software understanding, is when you don't understand how something is put together, be it a piece of software or a multi-part system, then its behavior will surprise you. You'll get vulnerabilities that you didn't know to look for. You'll get areas of exposure or information leakage that you didn't know about, and you'll get failure modes that you didn't even know to expect or even fear, right? And one thing that kind of put me in this mode, and I've been talking about this area for a couple of years, is I had the privilege to be, for 4.5 years, the technical director of the Capabilities Directorate here at NSA, and that's the directorate that builds all our big systems, including the US SIGINT system, which, no surprise, is a massive composition of stuff, old, new, borrowed, blue, etc. And during my tenure, it constantly surprised me with the ways that it could fail. And so, and a lot of that was because of the way the pieces went together, right? And you'd find some dependency you didn't expect or what have you. So we need, in my view, a better way of composing things to gain assurance here in my world, national security systems, in critical infrastructure, in critical private sector, and transportation, automotive, all those areas. A scientific foundation for secure composition. So the first question you could reasonably ask is, what is secure composition? And I did do a literature search before giving this talk. I won't say it was an extensive one, but I tried to at least do due diligence, and I could not find a good definition. I could find lots of system engineering definitions that were about composition in general, but I couldn't find a good one for what it meant for a composite system to be a secure composite system. So I made up my own, and certainly open to debate. But as we're going through this talk today, this is sort of the definition I'm working off of, right? And that is, we know, or we can compile a list of the security behaviors or guarantees or invariants that we require of the system as a whole, right? Of the composite, right? Which might be different than what we're expecting from each component in it, right? That we have some information about each of the elements. They're not, utter unknowns, and the interactions that they, use, that they interact, how they interact. And that we can show at least some of the overall security requirements are met by the composite. And for those where we cannot show them, we can tell why we can't show them. We can point to the missing knowledge that prevents us from showing whether a particular requirement or guarantee is satisfied. Now, you're probably thinking, man, if we actually had all these things, we'd be in great shape. And I agree. This is very much an aspirational definition. But I think it's something to strive for, right? Our knowledge of each component in a composition will always be imperfect, right? You're never going to have utter, complete understanding of some, huge piece of open source software, what have you. But this is saying that we know some of it, and for the rest of it, we have some understanding of what we don't know. So that's the definition I'm going to be working off of. Okay. Next, I'm going to talk through several types of composition. These are certainly not exhaustive, but I think they're ones that show up a great deal in practice and serve as a conceptual framework for what are the sorts of compositions we'd like to be able to assure, or where we would like to be able to securely compose these pieces. All right, so I'm going to hit these four. First one is layering. You see this all the time, right? And this is a composite where each layer depends on the one beneath it and provides services to the one above it. You will, of course, see layers being skipped, but that's supposed to be minimal. And there's usually some sort of contract that each layer offers to the one above and a set of requirements it has for the one below. And this just comes up a lot in practice. So, in this diagram, we're showing perhaps some kind of web system, like a web reporting system. The day I was working on this, I had gone to a meeting about the future of reporting systems, so it was on my mind. So, you got this application that users want to use, and they want certain security guarantees out of that application, out of that mission function. But that's living on top of some web framework, which is living on top of some language runtime, which is living in some form of container or resource manager, which is sitting on an OS, which is sitting on a hypervisor, which is eventually sitting on a processor. And then somewhere under there is physics and stuff. And I'm a software guy. I don't worry about that. So the interesting thing about this form of composition is that you have these assumptions. It's quite well structured. You have the ability, or perhaps the aspiration, to minimize jumping across layers, right? Like the language runtime should not be directly invoking the hypervisor. But there are still many mechanisms for surprise, okay? If a lower layer fails to implement some expected guarantee, then the upper layers may do things that you didn't expect, or react to external stimuli in a way that is undesirable. For example, Docker is supposed to guarantee that stuff running inside the container can't access the file system of stuff that's outside the container. And we've seen plenty of examples in the past where the container either had a bug or was misconfigured. It did not impose that guarantee, and the layers above it could run amok. All right. There's also the case where if a lower layer has some undocumented service or a flawed service, then you could have similar surprise, right? A good example of that would be a language runtime here the example is Java. It's supposed to provide strict memory safety guarantees. But there was a whole series of bugs a few years back where a unsafe compression library was embedded in Java, and those guarantees were broken. Right? So you couldn't make all the guarantees you'd like about the layers above it. Right? So those sorts of, if we had a science of putting together, let's say, just layering, even not all of composition, if we could even do secure, scientifically rigorous layering, we could make assertions about what each layer is supposed to provide, and then test those things to make sure that they were in fact being provided, and where they weren't, we would know where our mitigation work could be directed, right? And you could also say, well, maybe there's something that the container service isn't doing for me, and that tells me I have a gap, and I can go seek to rectify that gap by improving the container system or adding something to it to provide those additional guarantees. Okay, next model. Interesting. Where did that color palette thing come from?
That's a great question.
Oh, that's interesting. Okay, we're gonna ignore the color palette. I think this is supposed to be an animation, but whatever. So life cycle is one I definitely wanted to bring in as composition, because it's not all about a point in time. Sometimes it's about extent through time, right? That is a form of composition as well. If I'm writing a piece of software in the classic old waterfall model, I'm going to specify it, I'm going to generate some code, I'll compile that code, I'll package up the code, I'll run it through some, if I'm being a good doobie, I'll run it through some unit testing and integration testing, and then I'll deploy that code, right? And so different pieces and components are used in some of these different steps, right? There might be a specification tool that's only used in step one, or a specialized code generator that's only used in step two, or a user interface or a software development tool only used in step two, and so forth. There was a case few years ago where a test tool suffered a supply chain attack, and it was doing things it wasn't supposed to do. Now, that was a supply chain attack, which is a little bit out of scope here, but so you can think of this across time as a form of composition as well, right? If I want certain security guarantees in my software when it is ultimately deployed, what do I have to require of the packaging tool, the compiler, the code generator, etc. Right? Let me see if there's anything else in my notes I wanted to hit on that. Oh, and sort of looking ahead to the next one, the steps here that have a star on them, in modern software development life cycles at least, one or more of those steps will often automatically satisfy dependencies without even telling you about it, or at least not seeking your consent. They might print a message, yeah, I'm going off and getting these 79 other packages that you think you need, or that I think you need, and I'm bringing them in and packaging them up with your software. So those steps contribute to the final thing, right? There's this very seminal paper, I think it was from Kernighan years ago, Reflections on Trust and Trust, where he hacked the C compiler to generate compiled programs that had exploits in them. Or malicious functionality in them, right? And we've seen that more recently with a supply chain attack on Apple's Xcode development environment a few years back, right? Where everything you compiled with that version of Xcode had malware in it. So there are all sorts of issues that can occur here, right? Are you getting dependencies from the right places? Are there assurance steps involved here, like signing, and what are the security guarantees associated with that? It might appear, for example, in step 4, packaging. Are there default or injected credentials, and what are the security requirements surrounding those? Often see that in the test stage, where you have to have some credentials in order to perform the test. So, extent across time can be a form of composition as well. Okay. Next one is sort of the granddaddy of them, and that's dependencies, right? So in a fair bit of the literature that I looked at during my brief literature search is dependencies can be expressed as a directed graph. Right? And here's a very simple one. This is adapted from a diagram of a real app that I found out on the internet. And the real one, although it purported to be for a very simple Android app, was so complex that it would not fit on the slide at a reasonable font size. So I made up this notional one instead. But this is pretty simple. You've all seen this sort of thing before, right? You have some app and it uses a web framework and it connects to a database and it sends messages on a message queue. And some of the pieces have to do logging. And understanding what each of those arrows mean. Right? What is it that the web framework is expecting or requiring from the persistence engine? And what is the persistence engine requiring of the data encoder and of the storage layer? We don't tend to look at that in any kind of rigorous or scientific way. Now, I did see some papers that did try to look at this in a rigorous way, mostly by modeling information flow. You can take each of these arrows as well. There's some flow of information from the application to the web framework, and then there's some flow of information back when the web framework is finished doing some of its work. And that's actually a pretty reasonable way of modeling this kind of stuff. It's not necessarily the only way, but it's a good way. But what I didn't see in those papers, and maybe I didn't read them deeply enough, could be my problem, was understanding how you compose all this together so that you have some provided behavior down at the storage bubble, which is the lowest one here. And how does the fact that storage performs this one particular security guarantee, how does that affect persistence, which affects web framework, which affects application? And then you get certain emergent or aggregated behaviors that apply to the entire composite system. So you could certainly make statements about where the information goes, right? And that was the intent of at least one of the papers I looked at, was they wanted to see, well, could you have some information that's supposed to stay over here? Could it end up going over there? And information flow is great for that, right? Because you can apply with rigor, did that information ever flow from here to here to here to here? It's a really good model. But it didn't seem, at least in my brief reading, to be able to allow me to make assertions sort of about the entire composite system, which is, I believe, ultimately what we need to do to really say we have secure composability. Right? And I'm going to turn that around, actually. I like that word composability. It's fun to say. If I want to have, say, a persistence layer, right? Persistence framework is a bubble on this chart. Then I need to know a fair bit about that in order to compose it with other things, right? I could say this implementation of the persistence layer has good composability because it has really good API contracts and it implements them really and it doesn't do wacky things off to the side that I don't expect it to, and it's highly composable. And that is great guidance for whoever is going to be writing that persistence layer, right? And that is very valuable. But I'm sort of looking more at the other direction where I have these components, some of which I get to choose, others of which maybe I'm stuck with because it's a legacy system or it's a required part of the operating system or cloud vendor that I'm working on. And how can I take those, some of which are more composable than others, how can I take them and start to make well-founded assertions about the entire aggregate? Right? Let me see if there's anything else I wanted to say about that one. Wow, I wrote a lot of notes about this. Um, uh, this is, I'm going to spend a little extra time on this one because it's really important. Modern software has just exploded in how much of this it has, right? I one time was working with a company that worked in this space that would look at your software in a number of languages, and it would draw this effectively dependency diagram for you. It drew it in a different graphical representation, but it would derive this by basically watching the build process, and it would find these relationships, which is good. It's really, really good tool. They would, for demos, they would point it at typical pieces of open source software, and they would ask you, the customer, hey, pick a piece of open source software. I picked one. Pretty common, widely used across different parts of national security. And it had well over 500 dependencies, out to 7 layers deep, which at that time was as deep as the tool would go. I don't know if it might have had more, if I could have gone out to more layers deep. This was several years ago. I mean, the number of dependencies is far greater than like a normal software developer can hold in their head. So, and some of those, I'm quite certain the authors of that particular tool did not realize they were getting, right? Because they just said, oh, I need something to, like, I don't know, parse XML. So I'm just going to load this XML parser. And they didn't know the XML parser had like 19 dependencies of its own, right? And the primo example of that in recent history is Log4j vulnerability, right? And that's why I put a logging bubble on here, right? Because lots and lots of applications have to do logging. And what people didn't realize about Log4j, they're like, oh, I'm going to do logging. It's going to take my log message. It's going to write it into a file. What could be dangerous about that? They didn't realize that Log4j reached out to a full service remote directory framework that in turn reached out to a full service remote dynamic execution framework. And if you wrote a log message with particular stuff in it, it would try to do a directory lookup with code it didn't have. It would go and get that code and run it in your environment without ever telling you. And that was the essence. I'm oversimplifying. Those of you who know Log4j, please forgive me for oversimplifying. Is how you would end up running code by an attacker inside of your application because you didn't think the logging framework had directory lookup functionality or remote dynamic code loading functionality in the logging framework. Okay. So, right, you'd like to be able to make rigorous assertions about the logging framework that it only writes to files or whatever it is it's supposed to do. And if it did more than that, right, if it had the ability to do dynamic directory lookups, that would be propagated through this graph. So that at the end, your application would, your analysis of your application would say, oh, by the way, you are going to be doing dynamic directory lookups based on your user input. And then you would go, what? I didn't want to do that. That's not part of my requirements. And then you could presumably track it down and see why that was the case. Okay. So I talked about information flow. There's lots of other ways to represent these edges in this graph. You could think of them as API calls or network service transactions or storing information and retrieving it. All sorts of ways, and which way, there's no one best way. They're all good for different situations. All right, so I talked about the log4 shell, log4j example. There are lots of other examples. Something else I should mention is that, with these dependencies and automatic satisfaction of dependencies, it creates a form of attack surface. So it's really very important that if you think you're getting, a particular database framework, that you really know you're getting that one and not some malicious one with a similar name, which is apparently is quite an issue in some code repositories these days. Okay, so I talked about commercial products, right? So let's go to the next slide so I don't run out of time. That was meant to be a cool graphic transition. The next form of composing I want to look at, or composition I want to look at, is hybrid, where I'm defining hybrid as a system where some portions of it, some components operate under one security model and some components operate under a completely different independent security model. Okay, thus the term hybrid. And in this case, this is one you see all the time these days. You have some portions of your system are running enterprise on-prem, so they're under the security model you enforce within your enterprise. And then there are some portions that operate within a commercial cloud. And you're really living under the security model that the cloud provider offers to you. And it's part of their service that you get a certain security model with certain way of doing, authentication and logging and everything else. Right? And hybrid is tricky from the point of view of secure composition, because you don't have just one set of sort of axioms or postulates about your environment. You have at least two such sets that sort of by definition, the way I've sort of hand tweaked my definition here, they are different. So, when I, in the end, I want to get up and make sort of assertions about this entire composite, portions of it are resting on one set of foundations, parts of it are resting on a different set of foundations, and some parts are resting on both. Like the application bubble quite clearly depends on both the foundational assumptions of cloud and the foundational assumptions of enterprise on-prem, right? Because that's where it's getting its database and its message queue and other services. Okay, so there are other forms of hybrid system. Another one I would cite might be a typical space system, right? You have some of the software running on the spacecraft where it has certain security assumptions, and one assumption that people often make is that nobody can gain physical access to it while it's operating. But it also has assumptions like, it can get blasted by radiation and have a bunch of bits flip, and you got to be ready for that. And then you have the ground system, which may be vulnerable to physical access, was not as vulnerable to radiation, and may be connected to the internet and other things. So I would say a typical space system is also a hybrid, right? The satellite itself is one set of postulates or axioms, and the ground system has a different set. Okay, and then you have seams between them. And this, I think, is a particularly interesting aspect for composition, is what do we need to do to make guarantees about security at those seams, right? Here it's that vertical line between the orange region and the blue region. You're crossing over a boundary between an on-prem system and a cloud system, or between a ground system and spacecraft. Those seams may be more exposed, right? Anybody can point a radio antenna at your spacecraft and attempt to send signals to it. Anybody can attempt to go to your cloud database and try to call its API. Hopefully they'll fail, right, if they're not authorized. But how do you express those guarantees in a rigorous way so that you can then see, well, are my desired properties of that database bubble? How can I satisfy those with the security foundations that my cloud provider has given me? And can I satisfy them? And if not, what do I have to do differently? Okay. And then if my cloud provider sends me an email saying, oh, by the way, our way that we secure databases is changing as of next month, new behavior will be X, Y, and Z. How does that affect my composition, right? Some of the assumptions that I just based it on have just changed. All right. So let me go to the next slide. There we go. Sorry about the somewhat small font on here. I got a little carried away with this list. So, I'm sort of saying we need a science of secure composition. What would some features of such a science be? First of all, and it's numbered 0 to sort of emphasize that it's very fundamental, is we need some formal structure or way of expressing or describing these security dependencies. And I did not do a deep enough literature search to know if maybe some folks have already proposed mechanisms for doing this. They may be out there, but we definitely need something like that, right? Because all the others sort of depend on that. Then we need, I believe, some sort of taxonomy of composable behaviors, right? You might desire a very high level behavior of no unauthorized person can get to data in my aggregate system. That's a very high level statement. It's the kind of thing that mission owners want to be able to say, right? Well, how do I break that down into a set of lower level properties or constraints that I can actually sort of rigorously specify and check? You're going to need, I believe, mechanisms for expressing those behaviors or properties or invariants on the individual components in a manner that supports a composition analysis of putting them together. Okay. Then you're going to need an efficient means for notating this, and I say efficient because I'm assuming that some of these checks we'll want to perform in an automated fashion because of these systems being large, and therefore we need a means of doing that that is amenable to automating at scale. We need some practices or rules about how you combine low-level properties in order to create higher-level guarantees, and then how you propagate those through a dependency graph, whether it's a very simple linear graph like the layering model or a much more sort of general directed graph like our third model, the dependency model. I deliberately didn't say directed acyclic graph because I'm pretty sure some of these probably have cycles in their dependencies. We need analytic methods to identify gaps or problems, right? If I have to say to that mission owner, I cannot guarantee to you that no unauthorized person can get to the data in your system. Well, what do you need to fix in order to make it so? So I need an analytic method to identify that for me. And then finally, in the spirit of automation, I think it would be very important to have some formalism or some process that could generate tests, right? Both tests on the components to check whether a behavior that a higher level property of the aggregate depends upon is in fact being provided. Right? I'd like to have more faith in that than simply the vendor or open source project's assertion. Oh yeah, there's no dynamic code loading in this logging system. Oh, okay, thanks. I'd like to actually test it maybe. And then tests for the overall system that can validate that the composition has been assembled correctly, right? I have certain belief about how the requirements are composed, and I might need tests that validate or confirm those beliefs, or perhaps turn around and seek to refute them. And then, if I can hand it to a theorem prover and it can't find a refutation, then I might have greater confidence that the composition was successful. Okay. Yeah. Another property I wanted to talk about briefly on this slide was the notion of non-bypassability. And this has been, a big deal in a lot of secure systems I've worked with over the years, that, you have your controls in place and they check everything for access or integrity or whatever checks they're going to perform. And then you find that there's a way to go around them entirely and get directly to the underlying data or functionality that you're trying to abuse. And you'd like to be able to make assertions about that certain types of bypass can't happen, or if they do happen, they'll always be detected, something along those lines. Because if you can bypass some of this stuff, then sort of all bets are off, right? Okay. So to conclude, and I'm trying to finish well ahead of time so we have time for Q&A or even arguments. If you think of what I'm saying here is completely off base, now is a great time to say so. I assert that modern systems are overwhelmingly composites if this appeared on Wikipedia, it would probably have that citation needed thing after it. But I'm sure I could come up with citations. At least in the open source world, there have been statistical studies of how many dependencies things have. And one could use that as statistical basis for this claim. I believe that great strides have been made in building up individual components that are more secure, that offer security guarantees, right? Just look at progress lately in, secure access controls and memory safe languages and all sorts of other stuff that folks have worked on. In fact, probably some of the people on this call have worked on in being able to make strong security assertions about individual libraries or programs or modules. Those things are very valuable. The next step is to be able to extend that, to extend those assurances up from highly assured individual components up to the mission level through composition. And I would be remiss being here at DoD if I didn't say that we also have compositions where the individual components are not as secure as we'd like them to be. And to my mind, that's perhaps the hardest challenge in this space, is to be able to build up a system as a composition that offers guarantees that individual components cannot. In fact, I even have a mug with this on it, because it's such a big deal for our program here called Commercial Solutions for Classified. And Commercial Solutions for Classified is all about composition. Every one of the core security mechanisms has to be handled by two independent mechanisms. And we actually check that they're independent, and if they're not, we reject it. So, and that was a rule of thumb, right? We didn't have this rigorous science. So we adopted this rule of thumb. We got to have at least two, and they got to be independent, right? Because that's what we had, right? But we'd like to be able to make stronger assertions about that, okay, I only have partial trust in each of these components, but when I put them together, I have confidence that at least two independent failures are necessary before the overall system's properties will fail. Okay, so that's even kind of even a harder step, right? So all of you as researchers in the science of security, right? I feel like this community is the best place to make this challenge or to undertake research that would allow us to address this challenge, because you're used to thinking about security in a rigorous and scientific and falsifiable way. So that is it for my slides. And I welcome any questions or comments or refutations or whatever.